Okay, Jasmine, thank you. Good morning to one and all. Greetings from Adarsh College for Women. The Department of Chemistry and IQAC is organizing an 8-day state-level webinar series on selected topics in chemistry for CSCR NET, SET, GATE, IIT JAM aspirants. 6 eminent speakers from diverse fields in chemistry have honored us by delivering lectures. On day one, we had Professor S. Srivatsan, retired professor of chemistry, Guru Nanak College, who presented on spectra of metal complexes. On day two, Dr. S. Kabilan, retired professor of chemistry, Annamalai University, delivered a talk on retrosynthesis. On day three, Dr. S. R. Beater, former head, Department of Chemistry, St. Joseph's College, Trichy, presented on application of IR spectroscopy to metallic carbonyls. On day four, Dr. S. Swarnalakshmi, retired professor of chemistry, Guru Nanak College, delivered a talk on group theory. On day five, Dr. R. Kumaran, assistant professor, Department of Chemistry, DG Vaishnav College, discussed ESR spectroscopy. On day six, Dr. S. Balasubramanian, retired professor, Department of Inorganic Chemistry, delivered a talk on bioinorganic chemistry. On day 7, that is today, Mr.A.Gopalakrishnan, Assistant Professor, Department of Chemistry, DG Vaishnav College, will present on exactly solvable quantum mechanical systems at a glance. On day 8, Professor S. Swarnalakshmi from Guru Nanak College will discuss pericyclic reactions. We are very happy to have Mr. Gopalakrishnan with us this morning. Welcome you, sir. Anna Adarsh College for Women is a premier self-financing education institution located in Chennai. The college has been re-accredited with prestigious A+ grade in the second cycle of NAC accreditation. Department of Chemistry was started in 1986, offering undergraduate program with 2 staff members and 17 students. The department was upgraded to the postgraduate department in 2010. At present, 10 staff and 175 students belong to the department. Admissions are open for the academic year 2020-21. The department has signed 7 Memorandum of Understanding with industries of national and international repute. The department has excellent academic record and has produced university ranks, including first ranks, consistently. The Department of Chemistry has adopted effective teaching learning methods and assessment process. The objectives of imparting education is achieved through teaching activities, learning experience from students' perspective, and evaluation. Teaching activities involve lecture sessions, presentations, videos, models, and demonstrations. From the perspective of students, the students involve themselves in verbal learning, chain learning, and through seminars. Seminars and conferences are organized to expose students to the recent advances in the field of chemistry. The students are taken for industrial visits to get ideas about instrumentation techniques. The evaluation of students is done on the basis of internals, assessments, and seminars. The department strives for excellence, and this is seen by the way of organizing seminars, workshops, conferences at national and international level. This year, due to pandemic situation, we have materialized this webinar series for the benefit of students aspiring to clear competitive examinations. Alchemy is an intercollegiate event organized every year wherein large number of students from different city colleges participate. During this event, the in-house magazine Spectrum is released, which is a compilation of scientific articles by the students. The magazine Spectrum is by the students, of the students, and for the students. A very pleasant morning to all. I, on behalf of Department of Chemistry and IQAC, welcome you all for the day 7 of our webinar series on selected topics in chemistry for CSIR NET, SET, GATE, IIT JAM aspirants. As Dr. APJ Abdul Kalam rightly said, all of us do not have equal talent, but all of us have an equal opportunity to develop our talents. I rightly foresee this platform as a milestone in your lives. This platform has provided you opportunity to listen to very eminent teachers who are all masters in their own field. I hope that all the participants have learned tremendously from this webinar. This morning, we have a very learned speaker amidst us, Mr.A. Gopalakrishnan, Assistant Professor, Department of Chemistry, D.G. Vaishnav College, who will speak on exactly solvable quantum mechanical systems at a glance. Welcome, sir. I now request Dr. P. Shanti, Associate Professor, Department of Chemistry, to give the welcome address.
Thank you, Sandhya. A warm good morning to all. On behalf of our Management Punjab Association, Principal Dr. R. Shanti, Director Management Studies Dr. Jayashree Ghosh, Department of Chemistry and IQAC Anna Adarsh College for Women, I extend a warm welcome to each one of you present for the 7th day of our state level webinar series. It is my immense pleasure to welcome our today's speaker, Mr. A. Gopalakrishnan, Assistant Professor, DG Vaishnav College, who kindly accepted our invitation to be part of our webinar. Mr. Gopalakrishnan is a committed teacher whose dedication for learning is inspiring to any student. Apart from his college assignments, he is also involved in coaching students for various competitive examinations. I am sure today's session will provide an opportunity to participants to benefit from his experience of coaching CSIR aspirants. Today, Sir will deliver the lecture on exactly solvable quantum mechanical systems at a glance. I once again wholeheartedly extend my warm welcome to all the participants to our webinar. Thank you.
Thank you, ma'am. May I now request Mrs. Shobana Premlata, Assistant Professor, Department of Chemistry, to introduce the speaker.
Thank you, Sandhya. A warm good morning to one and all present. It is my honor to introduce our today's speaker, Mr. A. Gopalakrishnan, Assistant Professor, DG Vaishnav College. Mr. Gopalakrishnan has an experience of 17 years in teaching both undergraduate and postgraduate students. Quantum chemistry, group theory, statistical thermodynamics are his forte. He has delivered lectures in various colleges in Tamil Nadu. Sir is also a resource person at Dr. Ramasubbu Jayaraman Science Foundation, which is a non-profit organization which helps PG students in science in their effort to find a place in higher studies, research, etc. Teaching is not a profession, it is a passion. With dedication and passion, a teacher can transform students' aspiration into achievements. Mr. Gopalakrishnan, for the past 11 years, conducting coaching classes for CSR, NET, SET, GATE exams, and his classes have helped many students to clear these competitive exams. This pandemic situation has not stopped Mr. Gopalakrishnan from pursuing his passion for teaching. He has conducted online courses on topics like confirmation analysis, group theory, and computational chemistry for the benefit of the students. We are happy to have teacher like Mr. Gopalakrishnan among us to deliver the lecture on exactly solvable quantum mechanical systems at a glance. I hope the participants will utilize this session to the fullest. I welcome you all.
Thank you, ma'am. May I request Gopalakrishnan sir to deliver his
Hello.
lecture? Yes, sir. Over to you, sir.
Thank you, madam. Hello, everyone. Good morning. I would like to thank Dr. Shanti, head of the Department of Chemistry, and all other organizers from Adarsh College for giving me this opportunity to share some of my views in quantum chemistry. Okay, let's get into the topic. So my today's topic is exactly solvable quantum mechanical systems at a glance. Before going to see exactly solvable quantum mechanical systems, first I'll introduce the quantum mechanical postulates. Okay, our scientists have designed this quantum chemistry in a very beautiful manner, even for beginners. Right, can learn the subject in a very easy and simple way. Okay, so first let me start with the postulates in quantum mechanics. This is the first postulate. The state of a quantum mechanical system can be described by a function called wave function psi. Listen, first of all, what is meant by quantum mechanical system? What is meant by quantum mechanical system? Listen.
Sorry to interrupt you, sir.
Yes,
Your
madam.
screen is not visible, sir.
1 second, madam. Screen is not.
Yes, sir. It is visible now, sir.
Okay. Okay. Am I audible, madam?
Yes, yes, sir. You are audible.
Yeah. Okay. Right. So, quantum mechanical systems. What are quantum mechanical systems? Actually, microscopic particles like atoms, molecules, electrons, protons, okay, they are all called as quantum mechanical systems. The state of a quantum mechanical system, which means whether the atom is present in ground state or any of the excited states, okay, so the state in which that quantum mechanical system is present can be given by a function called wave function. So wave function will give you the state in which the quantum mechanical system is present. Okay, and the ultimate goal of quantum chemistry is to find the wave function psi. Okay, this is the most important one in quantum mechanical system, right? If any system is given, if any molecule is given, the ultimate goal is to find the wave function for the molecule. Okay, why we are particularly concentrating on wave function? Because wave function has all the informations about the system. Okay, all the information is about the total energy, kinetic energy, potential energy, linear momentum, angular momentum, position. Okay, so many informations about the particles, about the quantum mechanical system is present in the wave function side. So if any quantum mechanical system is given, the ultimate goal is to find the wave function for the system. Okay, then this wave function depends on coordinates x, y, z, and also depends on time. If a wave function depends on time, we call that wave function as time dependent wave function. Okay, and this wave function has an important property that actually we know very well. Wave function doesn't have any physical meaning. Okay, whereas the psi star into psi, this product, okay, tells you about the probability of finding the particle in a particular location. Okay, so this is postulate 1. So postulate 1 tells you about the state of a quantum mechanical system, right, which is given by the wave function psi. Then postulate 2. So I have told you all the informations about the system, quantum mechanical system, is present in the wave function. Okay, now how to get the information from the wave function? Suppose if I want kinetic energy of the system, or if I want angular momentum about the system, okay, how to get that? To extract the information from wave function, okay, we need some operators. Okay, so what are operators? Operators are some mathematical entities. Okay, what are operators? Operators are some mathematical entities. Say, for example, square root. Taking square root is an operator. Similarly, taking square is an operator. Okay, so these are all mathematical operators. But in quantum mechanics, all operators are not allowed. In quantum mechanics, we need some special operators called quantum mechanical operators. What are these operators? Quantum mechanical operators must be an Hermitian operator. Okay, all quantum mechanical operators must be Hermitian operators. Why do we need this Hermitian operator? Because see, we are going to measure or we are going to find the measurable properties of the system. Linear momentum, angular momentum, these are all measurable properties. So if you want to find a measurable property of a system, then we must use an operator that should give only the real value for the property. Okay, so to get the real value for the property, we need Hermitian operators. Okay, participants, keep this in your mind, very, very important. In postulate 1, I told you that wave function has all the information. Okay, wave function has all the information about the system. But to get the information from the wave function, we need operators. And there are so many operators available in mathematics, but we cannot use all these operators as such in quantum mechanics, because in quantum mechanics, right, we measure, we determine some measurable properties from wave function. The measurable properties should be always a real value. So to get a real value from the wave function, we need a special operator called Hermitian operator. Okay, right. Then here I have given some few examples of operators, right? X operator, Y operator, Z operator. These are all called position operators. Then Px, Py, Pz. These are all linear momentum operator. Okay, listen. So what is Px? Px operator is nothing but h by 2 pi I dou by dou x. Okay, so this operator will give you the component of linear momentum along x-axis. Okay, similarly, we have component of linear momentum along y-axis, component of linear momentum along z-axis. Then we have operators for angular momentum. Okay, then we have the Hamiltonian operator h. What is Hamiltonian operator? Hamiltonian operator is nothing but the total energy of the system. Okay, it gives you the total energy for the system, which consists of kinetic energy and potential energy. Okay, so Hamiltonian operator is nothing but total energy operator, right? Okay, so if you apply these operators, right? Suppose I'll take some operator A. If you apply this operator to the wave function psi, okay, we will get the value corresponds to the operator A. Suppose if I apply a linear momentum operator, say px operator on the function psi, then I will get the linear momentum for that system. Okay, in the state psi. Are you able to follow? Listen, if you apply a linear momentum operator on a function, okay, I will get the linear momentum for the particle. Similarly, if I apply Hamiltonian operator to the function, I will get the total energy corresponds to the particle in the state psi. Okay, so postulate 2 gives you about operators, and these operators, when you apply this operator to the wave function, you will get the required value corresponding to the quantum mechanical system in the state psi. Okay, then postulate 3. Actually, each and every postulate requires nearly 1 or 2 hours. Okay, so but I will try to give you the essence of the postulates. Okay, so without going into the details, I'm going to give you only the essence. Then this is postulate 3. Whenever you apply an operator to a function f, okay, some function f, right, it will give you some function g with some values. Suppose if you apply an operator to a function, if you get some other function, that is not at all important for us. Okay, whereas if you apply an operator to a function, if I get same function multiplied by some quantity, okay, see, I'm applying an operator to a function f. If I get the same function again multiplied with some quantity, okay, some constant a, then that function is called an eigen function. Okay, listen, actually eigen functions are very important, right, for quantum mechanical studies, very specifically for exactly solvable quantum mechanical systems. Okay, now listen, so what is postulate 3 says that if you apply an operator to a function, right, if I get the same function multiplied by some constant, then that function is called an eigen function, and that constant obtained is called an eigen value. Okay, it's called an eigen value. Right? What is this eigen value? Eigen value is nothing but this, right? Yeah. Eigen value is nothing but the measurable property corresponds to the operator A, okay, for the function f. I repeat, what is eigenvalue? Eigenvalue is nothing but the measurable property corresponds to the operator A, which means, suppose if I use Hamiltonian operator, then I will get energy as the eigenvalue. Suppose if I use linear momentum operator, then I will get linear momentum as the eigenvalue. Okay, so if I apply any operator to a function, if I get same function multiplied by some constant, then that function is called eigenfunction. That value is called eigenvalue. Okay, yeah. Now listen, whenever you apply an operator, quantum mechanical operator to a function, we always get, okay, an eigenvalue, right? An eigenvalue is obtained as the result whenever you apply an operator to a function, right? Then the next postulate, okay, here let me give one example for postulate 3. Let me give an example here. Yeah. See, suppose if this is a very important question in CSIR examination, they'll give some function, say for example here, I'll give some function 4 into e power minus 3x. Okay. Now, I'll give some operator, say d square by dx square. Now, the question is, what is the eigenvalue corresponds to the operator d square by dx square? when it acts on the function 4 into e power minus 3x. Okay, now how to find the eigenvalue? So what we have to do, apply the operator d square by dx square on the function 4 into e power minus 3x. Okay, so you have to differentiate 2 times. First I will do once. 4 is constant here, so keep it out. So I will differentiate once. If I differentiate e power minus 3x, I'll get 3 into e power minus 3x, right? Then 3 is constant, just take it out, so 12. Again differentiate one more time, so you'll get 3 into e power minus 3x again. Okay, now 12 into 3 is 36 into e power minus 3x. If you ask what's the eigenvalue, many students will say that 36 is the eigenvalue for the system. No, it is wrong. What you have to do, see the given function. The given function is not e power minus 3x. The given function is 4 into e power minus 3x. So you separate this as 9 into 4 e into e power minus 3x. Like this you separate. Because this is the given function, right? Then the remaining value is actually called the eigenvalue. So the eigenvalue for the operator d square by dx square, when it acts on the function 4 into e power minus 3x, is 9. Are you able to follow? It's a very important problem, because often student will commit this mistake. They'll put 36 as the eigenvalue, right? Yeah. So keep this in mind. Then now I'll go to postulate number 4. So this is postulate number 4. Postulate 4 is very, very important because it gives you the average value of the operator, or average value of the measurable property corresponds to the operator A for the given state psi. I repeat, what is meant by this? This symbol indicate average. Okay. Now we are going to find out average value of the observable correspond to the operator A in the state psi. Okay, this can be obtained using this formula. Okay, this is actually bracket notation. This bracket notation can be written in this way. So integral psi star A operator psi d tau divided by integral psi star psi d tau. This will give you the average value of the property. Property corresponds to the operator A in the state psi. Okay, what is the meaning of this? Listen, I'll explain with an example so that you'll get some clarity on this. Okay, let me take this example. Yeah, listen. Suppose I'll take some function psi, right, which is a normalized function. So, okay, I'll take some function which is a normalized wave function, and it is also an eigenfunction of the operator A. Suppose I have a function psi which is normalized, as well as it is an eigenfunction of A. If it is so, what will be the average value of the property corresponds to A operator in the state psi? Okay, this will be, is not, listen, see, I said it is an eigenfunction of A operator. What is meant by that? If you apply A operator to the function psi, I will get same function, because it's an eigenfunction, multiplied by some constant called eigenvalue. Okay, so if you apply the operator to the function psi, I will get some eigenvalue A multiplied by the same function psi. Okay, because it is an eigenfunction. Now, if psi is a normalized eigenfunction of the system, corresponds to the operator A, then the average value will always be equal to the eigenvalue of the system. Okay, if you measure the property associated with the A for the system in the state psi, we always measure whatever time you measure, you will get the value A as the result. Are you able to understand? So average value is nothing but the eigenvalue whenever the system is normalized. Okay, for the given normalized, and the wave function is eigenfunction for the operator A. Right? Suppose if wave function psi, it is normalized. Suppose if it is given like this, it is normalized but not an eigenfunction. Right? But it is given as linear combination of many eigenfunctions. Listen carefully. psi is a normalized function, but it is not an eigenfunction. But the psi it is given as a1 into phi1. Suppose I'll give like this, a2 into phi2. Okay, one second. I'll use some other coefficient. So C1 into phi1, C2 into phi2, C3 into phi3, etc., etc. Suppose if the function is given like this, okay, where the function is normalized, but it is not an eigenfunction. But phi1, phi2, phi3, they are all eigenfunctions correspond to the operator A. Okay, that is, if I apply the operator A to phi1, I will get the same function phi1 multiplied by some eigenvalue A1. Similarly, if I apply the operator A to the function phi2, I'll get, suppose if I get same function phi2 multiplied by some constant A2. So here what I'm saying, phi1, phi2, phi3, they are all eigenfunctions of the operator A. But psi is not an eigenfunction. In this case, what will be the average value? Okay, average value corresponding to the operator A. Average value corresponding to the operator A in the state psi. Okay, which is given as the coefficient square of the coefficient C1 square into the eigenvalue corresponds to phi1, that is A1, plus C2 square into A2 plus etc., etc. So this will give you the average value of A, okay, whenever the function is not an eigenfunction. Keep this in your mind, very, very important. Based on this, okay, till now no question was asked in the CSIR examination, but there are more chances to ask questions from this. Okay, so keep this in your mind, very, very important. I repeat once again, if the wave function is normalized and it is also eigenfunction of the operator A, then the average value corresponds to the operator A is always the eigenvalue. Suppose if the wave function is normalized, but it is not an eigenfunction, right? And the wave function psi is given as the linear combination of many eigenfunctions phi1, phi2, phi3, phi4, etc. Then the average value corresponds to the operator A in the state psi is given as C1 square. There is a coefficient, right? Coefficient square into A1 plus coefficient square into A2 plus coefficient square into A3, like that. If you add all these values, you will get the average value corresponds to the operator A in the state psi. Okay, keep this. This is very, very, keep this in your mind. It's very, very important. Okay, then. Now, I'll go to the next postulate. So this is postulate number 4. Okay, now postulate number 5. Yeah, this is very, very important postulate. Listen, I told you the ultimate goal of quantum chemistry is to find the wave function, because wave function has all the information about the system. Now, how to get the wave function? Right? To get the wave function, right, we have an equation called Schrodinger's equation. Schrodinger equation. Okay, so this is actually time dependent Schrodinger equation. Here I have given time dependent Schrodinger equation. So if you solve, Schrodinger equation is just a differential equation, right? So if you solve this Schrodinger equation, okay, you will get solutions as wave functions. Okay, you will get you will get many solutions, right? And you know very well what is meant by acceptable solutions and all. So I don't want to go into the details of all these things, but we can get the wave function by solving the Schrodinger equation. Here I have given time dependent Schrodinger equation, right? We also have time independent Schrodinger equation, which can be written as H psi is equal to E psi. This is the short way of writing time independent Schrodinger equation. Now, here I like to give an additional point. Listen, we know very well Hamiltonian operator is nothing but total energy operator, which is equal to kinetic energy operator plus potential energy operator. Suppose if potential energy is independent of time, I repeat, if potential energy part of the Hamiltonian, if it is independent of time, then the wave function psi, which is a function of coordinates as well as time, that can be separated into two parts. Okay, one part depends on coordinates alone, the other part depends on time. Okay, listen, this separation is possible if the potential energy part of the system does not depend on time. or it is independent of time. Okay, listen carefully, very, very important. Wave function depends on coordinate as well as time. Okay, but we can separate this wave function into two parts. Okay, one wave function, there is one part of function depends on coordinates alone, x, y, z, and the other part of the function depends on time. This separation is possible only if the potential energy part of the Hamiltonian is independent of time. Okay, and making use of this equation, we can also show that f of t is equal to e power minus iet by h cross. Okay, and what is psi star psi? I told you psi star psi will give you probability, right? Whenever potential energy is independent of time, then the psi star psi, okay, I just call it as big psi star. Okay, big psi star big psi is equal to psi star psi, right, which is time independent wave functions. Okay, these two are equal when the potential energy part of the Hamiltonian is independent of time, and this gives you, see here, this is actually probability. Now the probability is independent of time, right? Whenever probability or psi star psi is independent of time, we call that state as stationary state of the system, right? See, in the exactly solvable quantum mechanical system, right, we are going to see only stationary states, right, not the other states. Are you able to follow? Yeah, we have other phenomena like scattering. So many things are there where non-stationary states also possible, right? But whenever potential energy part of the Hamiltonian is independent of time, okay, then this psi star psi and this psi star psi, they are one and the same, and this is also independent of time. Okay, then whenever psi star psi is independent of time, we call that state as stationary state of the system. Okay, stationary state means the probability of finding particle at a particular location does not change with the time. Okay, the probability of finding particle at a particular location does not change with the time. That is the meaning of stationary state. Okay, then right. So first, let me start with a simple problem here. The wave function psi of a certain system. This is actually a question which appeared in the previous year's CSR examination. The wave function psi of a certain system is a linear combination of psi is equal to square root of 1 by 4 into psi 1 plus square root of 3 by 4 into psi 2, where psi 1 and psi 2 are energy eigenfunctions with eigenvalues non-degenerate E1 and E2 respectively. What is the probability that the system energy will be observed to be E1? See, it's a very simple problem, isn't it? Now we have two non-degenerate states. Okay, for this state energy is E1, for this state energy is E2. For this state the wave function is psi1, and for this state the wave function is psi2. Now we have a state, some state is given. We have a state which is given as 1 by square root of 1 by 4 times psi1 plus square root of 3 by 4 times psi2. Some state is given like this. Now the question is, in this state, what is the probability? What is the probability that the system energy will be observed to be E1? Okay, see, you know very well, psi1 corresponds to the energy E1. Therefore, this coefficient, no, take the square of the coefficient, that gives you the probability directly. I repeat, now a system, the system is present in some state psi, which is linear combination of these two, psi1 and psi2. Now the question is, what is the probability of the system, right, in the wave function psi, what is the probability of the system which will be observed to be E1? Okay, what is the probability of finding the system in this state? Okay, for that what you have to do is see the coefficients of psi1, take the square. The square of the coefficient will give you probability. So what is the probability? Probability of finding the system in the state E1 is the square of this. Okay, square of root of 1 by 4, which is 1 by 4. So the correct option for this question is 1 by 4. It's a very simple question. So if you want to find the probability, right, for a system which is present in a state, that state is a linear combination of many wave functions. Then if you want to find the probability for a particular state, for a particular eigenstate E1, then you can take the square of the coefficient. That square of the coefficient will give you directly the probability. Okay, It's a very simple question. Then now, before begin with the exactly solvable quantum mechanical systems, I like to give these points. Time independent Schrodinger equation, I have given this already. H psi is equal to E psi. Here, listen, if I put this symbol big psi, which represent, okay, the wave function depends on coordinate as well as time, But if I use this symbol psi, which means the wave function depends only on coordinate. Okay, yeah. So H psi is equal to E psi, right? This is the eigenvalue equation, right? Represent the Schrodinger equation or time independent Schrodinger equation. The time independent Schrodinger equation can also be written like this. This is the expanded form of the time independent Schrodinger equation. Dou square by dou x square, dou square psi by dou y square, plus dou square psi by dou z square, plus 8 pi square m by h square into E minus V into psi equal to 0. Listen, what is this equation actually tells about? Listen here, E is total energy and V is potential energy, right? If you subtract potential energy from total energy, we get kinetic energy. So this equation is applicable for moving particles, moving microscopic particles. Are you able to follow? Yeah, I told you microscopic particles are nothing but quantum mechanical system. Okay, in quantum mechanics, what is system? System is nothing but microscopic particles. Microscopic particles are called quantum mechanical systems, right? Here, E minus V will give you kinetic energy. That means this equation, this Schrodinger equation is applicable for moving microscopic particles, right? Yeah. And you know very well this dou square will give you the curvature, right? Curvature of the wave function, right? In terms of x, in terms of y, in terms of z. Okay, now, then the next important point is integral psi star psi d tau. If it is equal to 1, then we call that function as normalized wave function. Okay, so this formula, integral psi star psi d tau, if it is equal to 1, then the wave function is called a normalized wave function. Listen, in quantum mechanics, very specifically in the exactly solvable systems, we are going to see only normalized wave function. Why do we need normalized wave function? What's the necessity for normalized wave function? Suppose assume that a particle is moving in a particular axis, say x, okay, and it is moving or it is confined between some limits, say 0 to L. Okay, now what is meant by normalized? Listen, suppose if you measure probability at this point, 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 okay, you know very well, psi square will give you the probability. So you find the probability at different positions, right, inside the box, and add all the values. If you add all the values, if it is equal to 1, then we say that the wave function is normalized. But what is the meaning? The meaning is the particle never exists, okay, outside the box. The probability of finding the particle outside the box is 0. It means the particle is confined within the box. I repeat. Listen, what is the why do we need to confine the why do we need to the normalized wave function? Okay, the reason is when you do normalization, okay, it makes the particle present in the confined system. Okay, so now if you suppose if I take if I find the wave function for a particle inside a box, okay, and if I take probability, that is taking psi square value at different positions, and if I add all the values, right, I will get the answer as 1. If I get the answer as 1, then probability of finding the particle outside the box becomes 0. So whenever a system is confined, right, then the wave function corresponds to that system should be normalized. Are you able to follow? Because whenever it is normalized, okay, only when it is normalized, then only we can say that the particle is present inside the system or inside the confined position. Otherwise, the probability of finding particle outside the box also become non-zero. Okay, then another point, integral psi 1 star psi 2. Okay, this is wave function corresponds to one particular eigenstate. This is wave function corresponds to another particular eigenstate having different energy value. then integral of psi1 star psi2 d tau should be equal to 0. Okay, what does it mean? Okay, I'll give some more explanation here, which is very important. Yeah. Okay, listen. Suppose I have a system which has two eigenstates. For this, the energy is E1. For this, the energy is E2. Suppose. Okay. And for this state, let the wave function be psi1. And for this state, let the wave function be psi2. If psi1 and psi2 have different eigenvalues, okay, energy eigenvalues, then the integral psi1 star psi2 d tau should be equal to 0. Okay, the two states must be orthogonal to each other. I repeat, if the integral of psi1 star psi2 d tau is 0, then we say that the two states psi1 and psi2 are orthogonal to each other. Okay, then suppose if the two states, suppose I have a degenerate states, suppose this is psi1, this is psi2, these two states are degenerate. In this case, the integral psi1 star psi2 d tau, right, this is need not be 0. Very, very important. Okay, it may be 0 or may not be 0. It depends upon the states that you choose. Okay, listen, I repeat, if the two states have different energy eigenvalue, then the wave functions corresponds to the two states are orthogonal to each other. Orthogonal means the integral psi1 star psi2 d tau should be equal to 0. Suppose if the two states have same energy eigenvalue E, see, for the two states the energy is same. If they have same energy eigenvalue, then the integral of psi1 star psi2 d tau need not be 0. Okay, then I'll give some more information here, which is also very, very important for the CSIR examination. Suppose I'll take two electronic levels. Okay, this is electronic level E1. This is I'll take this ground electronic level E0, and this is E1. And you know very well, electronic levels have number of vibrational levels. Electronic levels have number of vibration levels, and each vibration level has number of rotation levels. Right, each vibration level has number of rotation levels that we know. Now, I'll take a vibration level, say V0. Okay, I'll take a vibration level V equal to 0 from the ground state. Okay, I'll represent clearly. I'll take vibration state, say V equal to 0 in the ground electronic level, and I'll take some vibration level V. I'm sorry. I'll take a vibration state V equal to 0 from the ground electronic level, and V equal to 1, right? Some excited vibration level from the same electronic level. Then, if I take the wave functions corresponds to these two vibration levels, see, psi V is 0, psi V equal to 1, d tau, this should be definitely 0. Whereas, if I take V0 from the ground state and if I take a wave function, vibrational wave function from the excited state, I'll represent these excited state wave function as double prime. Okay, just for our convenience. Okay, so this is the vibrational state of the ground electronic level. This is vibrational state of the excited electronic level. If I take the integral of this, okay, the product of integral of this is not equal to 0. Very, very important. Okay, listen. Within the same electronic level, two different vibration levels are orthogonal. Similarly, within the same vibration level, two different rotational levels are orthogonal. Whereas, if I take one rotation level from higher vibration level and another rotation level from different vibration level, okay, then those two rotational levels are not orthogonal to each other. I repeat, this is very, very, very important. Okay. Listen, see, suppose if we take a vibrational state, say V equal to 0 from the ground electronic level, and another vibrational state from the excited electronic level, it may be the ground vibration state or any other excited vibration state. If I take these two states, these two vibration states are not orthogonal. Whereas if I take two vibration levels from the same electronic level, then those two vibration states must be orthogonal to each other. Okay, so here this psi star V0, psi star V equal to 1 belong to same electronic level. Therefore, they are orthogonal to each other. Whereas here the psi star V equals 0 and psi V double prime from excited electronic level, these two vibrational states are not orthogonal to each other. So keep this in your mind, very, very important. Okay, orthogonality has lot of meaning. Okay, then okay, I'll go there. Okay, so I have given some informations about the orthogonal conditions. Okay, now we'll discuss. Here I have one more problem. This is a previous year examination question. An eigenstate of energy satisfy H psi n, H psi n equal to En psi n. Participants, is very important. In most of books, if you see, they'll put cap symbol for Hamiltonian operator on most of the operators. But nowadays, this cap symbol are not used, right, in many latest editions. So don't get any confusion there. Okay, even if the cap symbol is not there, it should be an operator. Okay, keep it in mind. So H psi n equal to En into psi n. What is this? When you apply an Hamiltonian operator for a quantum mechanical system present in the state psi, that is nth state, will give you the energy of the nth state and psi n. Okay, I'll read out the question. An eigenstate of energy satisfies this equation in the presence of an extra constant potential V0. Normally, when you do derivations, right, when you solve Schrodinger equation, in most of the system, what we do, we assume potential energy as 0. If you assume potential energy as 0, then you will get energy as En. Okay, suppose if potential energy is not 0, we have some value, say some constant value V0. See here it's given, is an extra constant. Whenever the potential is not 0, but it is a constant, then the energy of the state will become En plus V0. I repeat, very, very important. If you assume potential energy of the system as 0, then you will get energy of the state n as En. Suppose if the potential energy is not 0, but it is a constant, some value say V0, then the energy of the nth state can be given as En plus V0. Okay, so we'll see the options. See option 1, both En and psi n will change. Listen, energy will change, definitely energy will change, but wave function does not change. Psi n, it remains as such. I repeat, when the potential energy of the system is not 0, but it is a constant, then the energy value for each state will change. But the wave function corresponds to the state n never changes. Wave function remains as such. So option A is wrong. Then see option B. Both En and the average kinetic energy will change. Okay. Listen, En will change, but average kinetic energy doesn't change. Okay. Average kinetic energy doesn't change. Then option C. Only En will change, but not psi n. Yes, this is correct answer. En will change. Okay, not psi n. And see option D also. Only psi n will change. No, psi n won't change. So for this question, the correct option is C. Listen, what I like to say here is, whenever you assume potential energy as 0, you will get some formula for energy. But if the potential energy is not 0, okay, keep this in your mind. You have to add that potential energy to the to your formula. Okay, yeah. I'll give more information about this as we proceed. Okay, then now. Okay, then I have to say one more point here. That is a commutator operator. If two operators commute or not, how to check? For this, we use the commutator operator, which is usually represented as square brackets. Okay, within square brackets, right? So commutator of A and B is equal to A into B minus B into A. right? Suppose if I apply the commutator operator to a function say psi, then how to apply this operator? A into B into psi minus B into A into psi. What is the meaning? First you apply the operator B to the function psi, you will get some result. Then apply the operator A to the result, you will get the final answer. Similarly here, apply the A operator first, you will get some result. Then apply B operator to the result so that you will get the final answer. Then subtract these two, you will get the commutator value corresponds to A and B. Okay, this is the formula for commutator operator. But here, I like to give two important information which is very, very necessary for CSIR exam preparation. Suppose if the commutator of A and B is 0, what does it indicate? It indicates that A and B commutes. It indicates that A and B commutes. If it is 0, that means A and B commutes. A and B commutes means, what does it indicate? It indicates that, listen, A and B commutes, it indicates that the property associated with A and the property associated with B both can be measured simultaneously. We can measure both simultaneously with 100% accuracy. Yes, very, very important. If the two operators commute means the commutator value should be 0. If the two operator commutes, then the property associated with A and the property associated with B both can be measured simultaneously with 100% accuracy. It doesn't obey Heisenberg constitutive principle, right? If A and B, commutator of A and B is not equal to 0, then we say that the property corresponds to A and the property corresponds to B. Okay, we cannot measure them with 100% accuracy, right? Simultaneously. Okay, simultaneously we cannot measure both A and B with 100% accuracy. Yeah, it obeys the Heisenberg uncertainty principle. Okay, uncertainty principle. So listen, when two properties obeys Heisenberg constitutive principle, which we can easily find out by finding the commutator of the two properties A and B, or the two operators A and B. Okay, yeah. So I will give some more information here. I'll give some more information. Yeah. Listen, suppose we know very well, according to Heisenberg principle, Heisenberg uncertainty principle, we are very familiar with this equation. That is, it is impossible. This is the statement we'll give normally. It is impossible to measure position and momentum of a moving microscopic particle simultaneously with 100% accuracy. I repeat, it is impossible to measure position and momentum of a moving microscopic particle with 100% accuracy, right? It's not possible. So if you find the commutator of this, okay, you'll get some value for commutator. Okay, for this you'll get the commutator as I into h cross. Okay, you know very well what is h cross. H cross is nothing but h by 2 pi. Okay, if the commutator is not 0, okay, I'm getting some value here. It means these two properties, x means position, px means momentum, that is component of momentum along x-axis. These two cannot be measured simultaneously with 100% accuracy. Okay, see, with 100% accuracy we cannot measure, but if you try to measure both, you will get some error in the measurement of position and you will get some error in the measurement of momentum. Okay, these are all called as uncertainties, right? Uncertainty associated with the position, uncertainty associated with the momentum. The product of these two should be greater than or equal to h by 2 pi. This is what we call as Heisenberg uncertainty principle, right? Or mathematical formula of Heisenberg uncertainty principle. Now, I like to give some more information here. Suppose I'll take position x and momentum along y. Along y, if you see, this value is 0. Okay, so while using the term momentum, you should be a little careful, right? Why? Listen, the position along x-axis and momentum along x direction or x component of momentum, these two, they do not commute. So you cannot measure them simultaneously with 100% accuracy. Whereas if you measure position along x-axis and if you measure y component of momentum, these two can be measured with 100% accuracy. You can measure this with 100% accuracy. Okay, so try to understand these meanings. Okay, so similarly, say I'll give this formula: x comma px, right? Y comma py, then z comma pz. Okay, these are all equal to I into h cross, and x comma py, then y comma pz, then z comma px, right? These are all equal to 0. That means these can be measured simultaneously with 100% accuracy, whereas these are all these variables are also called canonically conjugate variables. These canonically conjugate variables, right, cannot be measured with 100% accuracy, right, when you measure both properties simultaneously. Okay, that's very important. Now, I'll give some more point here. Sorry. This is very essential. That's why I'll give some more point. See, suppose if I take some operator A and take a square or cube or some power of the same operator, they always commute with each other. Okay, these are some important property. Remember. Then I'll take the position x and the momentum px power some value n. What should be the value of this commutator? Which is equal to, okay, listen, we know very well when we have x and px, the value is I into h cross. Now I have px power n. I have px power n here. So what should be the answer? The answer is n in, n into px power n minus 1 into I into h cross. Okay, keep this I into h cross as such. Okay, bring this power n in front. So we'll get n into px power n minus 1 into I h cross. This is the value of this commutator. Okay, what you have to do? You have to apply the operator again. That's the meaning. Okay, yeah. Then similarly, this is very essential. See, x comma px is I h cross, right? If I write px comma x, okay, that is minus I h cross. Okay, so if you swap the operators, then the commutator value, the sign of the commutator value will change. Okay, very important information. Keep this in mind. Similarly, suppose if they ask like this, say px comma x power n, what is the value of this commutator, right? So now position is in the second place, right? Position is in the second place. Therefore, you should put minus I h cross. Okay, then n into x power n minus 1. This is the answer for this commutator. So keep all these things. We have very, very important informations about commutators. Okay, so what is the use of commutator? By analyzing commutation relation between two operators, we can very easily say whether the two properties associated with operator A and B can be measured simultaneously with 100% accuracy or not. Okay, can be measured or not, that we can say. Okay, then okay, now we'll go back. So this is where we left. Now, so here I have another question which appeared in the previous year examination. The value of the commutator of x comma px square is, I have given the formula just before, right? The value of the commutator x comma px square is very simple. Listen, position is front, momentum is back, right? Position is in the first front place, momentum is in the second place. If it is so, then the value of the commutator is I h cross. Keep it as such. First write it as, first write that first. Then px square is there. So 2 into px power 2 minus 1 is 1. So this is the answer. So the correct option is this, 2 I h cross into px. Are you able to follow? Very simple. If you remember these properties, you can easily answer these questions, right? Okay. And luckily, these questions, okay, they have given 4 marks, right, in the examination. Then now, so I have given some enough informations about how to go into or how to enter into quantum mechanics. Now I'm going to discuss about exactly solvable systems. What does mean by exactly solvable systems? It means we can solve the Schrodinger equation without using any approximation. Okay, so we can solve the Schrodinger equation h psi equal to E psi, right? We can solve the Schrodinger equation without using any approximation. That is called exactly solvable systems, right? So in that we have particle in a box problem, rigid rotor, simple harmonic oscillator, and hydrogen atom in the absence of any external field. Okay, particle in the box, which gives you the translational motion of the quantum mechanical system. Rigid rotor corresponds to rotational motion, and simple harmonic oscillator corresponds to vibrational motion. So we are going to see these three these three motions of the quantum mechanical systems first. After that, we are going to see hydrogen atom. I'm not going to do any derivations, but I'm going to give you some important results and the problems that appeared in the examinations. Okay, then. Okay, let me start with the particle in a box problem. I told you particle in a box, okay, gives you the translational motion of the particle, right? It describes about the translational motion, right? Yeah. So this translation motion, I will, okay. Before that, I forgot to say this information. Yeah. What is meant by a free particle? Okay. Listen, whenever any external force, or if no external force act on a particle, right? Suppose a particle is there, which is moving here and there. If there is no external force act on the particle, we call that particle as a free particle. So free particle means particle with no external force. No external force. Okay, no attractive force, no repulsive force, nothing. Right? A particle with no external force, then the particle is called a free particle. Then in translation motion, we have two motions. One is called free motion, the other one is called confined motion. What is meant by free motion? Yeah, just for understanding purpose, I'll say like this. Free motion means without boundary. Okay, when there is no boundary for a particle, then the particle can move from India to America, right? Then America to Japan, like that. There is no boundary there. Okay, when there is no boundary, then translational energy is not quantized. Okay, we are not going to study about quantization of translation energy, we are not going to study about the free motion here. Okay, because free motion doesn't give quantized translation energies, right? Then what is meant by confined motion? Confined motion means we are going to arrest the particle, okay, between a limit, between two limits. Okay, suppose I have some particle which is moving only in between these two walls, right? Then it is called a confined motion. Are you able to follow? Free motion means a particle is moving without any boundary; it can go anywhere. Right? It's called free motion. In the case of free motion, translational energy is not quantized. Okay, whereas in the case of confined motion, translational energies become quantized. Right? So in confined motion, translation energies are quantized. Let's keep this in mind. And we are going to see problems pertaining to only the confined motions. Right? Okay, let me start with the particle in box in one-dimensional model. So this is the heading, particle in one-dimensional box with infinite potential energy barrier outside. What's the meaning? Let us assume I have some particle which is moving along x-axis, so it is one dimension, right? And we have confined the particle between the two limits 0 and L. So I have two walls here. Okay, the potential energy on the wall and outside the wall, it is infinite. Potential energy on the wall, outside the wall is infinite. Okay, and inside the wall, right, inside, potential energy can be any value, but we can assume the potential energy as 0. I repeat once again, we had discussed the one important question, that whenever you assume potential energy as 0, then you'll get energy as En. you'll get some energy, which we are going to derive, right? The formula will give you the energy directly. Suppose if the potential energy is not zero, okay, that case also there. If potential energy is not zero, but it is a constant, then your energy for each state will get, okay, the sum of these two. The sum of these two will give you the energy of each state. Okay, yeah. So now we have a particle in 1D box where the particle is confined to move between the limit 0 and L. Okay, so the length of the box is L, right? And I'm going to assume that the particle inside the box as a free particle. If I assume the particle is free particle, then potential energy of the particle is constant. Okay, listen, if I assume the particle is a free particle, then potential energy become constant, right? And you can assume, since it is a constant, you can assume the potential energy as zero also, right? So if I assume potential energy as zero, okay, what will be the energy of the system? And listen, this is very, very important. Very, very important. Listen, this boundary condition, see here x is equal to 0, here x is equal to L. Often people will say that confinement leads to quantization. It is absolutely wrong. It is not the confinement that leads to quantization. It is the boundary condition that leads to quantization. Okay, what is meant by that? See, when x is equal to 0, your wave function becomes 0. Similarly, when x is equal to L, when your wave function becomes equal to 0. So at the boundaries, the wave function at the extreme position or at the boundaries, the wave function should be 0. This boundary condition decides the quantization. I repeat, quantization does not depend on how long you are confining the system, right? It does not depend on L. It depends on the boundary conditions, x equal to 0 and x equal to L. Okay, yeah, I'll give more information about this later. Now, so using this boundary condition for particle 1D box, we can solve the Schrodinger equation. Okay, we can solve the Schrodinger equation. If you solve the Schrodinger equation, you will get a wave function for the nth state, okay, which is given as square root of 2 by L sine n pi by L into x. Okay, and you will get the energy En as n square h square by 8 ml square, and value of n corresponds to 1, 2, 3, 4, etc. If I put n is equal to 1, I will get some energy. If I put n equal to 2, I will get a different energy. Listen, for n equal to 1, you will get some energy. For n equal to 2, you will get some energy. Between these two, many possible energy values are there, but those values are not accessed by your particle. Okay, the particle cannot access, right, all possible energies. It can access only the energies, okay, given by this formula. That means energy is quantized. Okay, I repeat, if you assume potential energy of the particle inside the box as 0, then this energy corresponds to kinetic energy. Because we are assuming potential is 0, so this energy corresponds to kinetic energy, also called translation energy. These translation energies now become quantized, right? Now, so remember these formulas. This is the energy for particle in 1D box with the infinite potential barrier outside, and this is the wave function for the states. And one more information, for box problem, 1D box, 2D box, 3D box, whatever it is, for box problem, the quantum number n cannot take the value 0. 0 is not allowed for any box problems, right? Keep this in mind. Then okay, so this is okay, so these are all the energy values corresponds to n equal to 1, n equal to, n equal to 3, n equal to 4, etc. Okay, when n is equal to 1, right, if you substitute n equal to 1 in the formula, you'll get h square by 8 ml square. So this is the energy corresponds to the ground state. Okay, then if you put n equal to 2, you'll get 4 times this value. I'll take this value as E1, right? Therefore, the value of this is 4 into E1. Similarly, if n is equal to 3, you'll get 9 into E1. If n equal to 4, you get 16 into E1. Okay, if you observe this carefully, listen, the gap between these two, that is the n equal to 1 level and n equal to 2 level, if you see the gap, if this is 4E1 and this is E1, What is the difference? The difference is 3e1. Similarly, if you go to n equal 2 level and n equal 3 level, the difference between these two is 5e1. Correct? 9e1 minus 4e1, it is 5e1. Similarly, here 16 minus 9, 7e1. Right? So what does it indicate? Listen, the energy levels, the gap between adjacent levels are not equal. In the case of particle in 1D box, the gap between adjacent levels are increasing, right, as we go to the higher values of n. Okay, so this is one important point. Then what is the gap between energy gap between two adjacent levels? Okay, energy gap between adjacent levels. Okay, that can be obtained using the formula 2n plus 1 h square by 8ml square. Those who are preparing for CSIR examination, right, keep this formula in your mind. Very, very important. To find the energy gap between any two adjacent levels, you can use this formula, and here you must substitute the value of n for the lower level. Okay, here n corresponds to the lower level. Suppose if I take two adjacent level for which n equal to 5 and n equal to 6, to find the delta E between these two levels, you put n equal to 5 in this formula. Okay, yeah, in this formula the n corresponds to the lower level. Okay, keep this in mind. Then these are all the wave function plot. Here I have given wave function as well as the square of the wave function probability plot. So the probability plot shows that for n equal to 1 level, listen, psi square is 0 at the boundaries, but it is not 0, okay, anywhere in between these two, in between the two walls, correct? That means there is no node, right, in the ground state. Right, see here in the first excited state, there is n equal to 2 level, right? The probability becomes 0 at the center. So it means it has one node. As we move to the higher levels, right, you will get more nodes, right? And we can give a general formula here: number of nodes is equal to n minus 1. Okay, for ground level, n value is 1. Put 1 here. 1 minus 1 is 0. So there is no node in the ground level. For the first excited level, n is equal to 2. Substitute n equal to here. 2 minus 1 is 1. So we have one node. Okay, so you can use this general formula to find the number of nodes, right, in particularly 1D box. Then, yeah, here I have given some important points. Average value of x. Participants, listen this carefully. Average value, x means position. On average, what is the position of the particle inside the box? On average, whatever may be the state, whether it is a ground state, okay, whether it is n equal to 1 or 2 or 3, whatever it is, always the average value of position of the particle, okay, is equal to L by 2. Right? Similarly, see in the examination they are asking question like this: what is the average value of square of the x value? Square of x, right? Listen, if you take square of x or cube value of x, okay, average of these, listen, then these values depends upon the quantum number n also. Okay, that's why whenever a question is asked based on this, they'll say that's one important information. They'll say that when n approaches infinity, what will be the average value of x square? They will ask question like this. Why? When n approaches infinity, then the formula doesn't contain n. I repeat, for the ground state, see for any n equal to, for any state, average value of x is always L by 2, no doubt. What is the average value of x square, average value of x cube, average value of x power 4? Okay, to calculate that, it is very difficult because the formula contains n value also, and you have to remember a formula for x square, x cube, x power 4 separately. But if n approaches infinity, that is when quantum number approaches infinity, then quantum concept and classical concept starts to merge. Okay, it's called Bohr's correspondence, right? So when m approaches infinity, okay, you can use the classical formula to find the value of x square. So what we have to do, listen. So what I'm saying, the value of right here, the average value of x square is, listen, the average value of x square is L square box length by 2 plus 1, 3. L square by 3 will give you the average value of x square under the limit n approaches infinity. When n become very large, then the average value of x square is L square by 3. Similarly, what is the average value of x cube? when n approaches infinity. When n approaches large, very large, or approaches infinity, you need not worry about n. You can write the average value directly. How? See here x cube, no? So put L cube by 3 plus 1, 4. Okay, this is the formula. You can write the average values directly. Listen, for x square, x cube, x power 4, we need this n power n approaches infinity. But for x, for average value of x, it is always L by 2. You need not worry about the quantum number n. Okay, then what is the average value of the momentum? Right, the average value of momentum, because listen, inside the box, the particle can move in the positive x direction, or it can move in the negative x direction. Right, since both the movements are possible, on average the momentum, right, is 0. Okay, on average, listen, momentum 0 means, listen, average momentum is 0. I'm not saying that particle is not moving. Then if px is 0, momentum is 0, then particle is not moving, it is static. Okay, I'm not saying this. What I'm saying, average value of momentum is 0. It means, listen, the particle can move in the positive x direction, or particle can move in the opposite direction, right? It can move in this direction or in this direction. Since it can move in both the directions, see, when the particle move in this direction, the momentum is positive. I'll put positive. Whereas the particle moves in the opposite direction, then the momentum is negative. Value of the momentum is negative, and the average of these will be 0. Okay, so remember, this is very important. Average value of momentum is 0 for particle in 1D box. Okay, then selection rule for electric dipole transition. Right, I don't want to go the details of this. The selection rule is this: delta n should be plus or minus 1, plus or minus 3, plus or minus 4, plus or minus 7, etc. Odd numbers are allowed. So in the transitions, in the transition, this is n equal to 1 level, 2 level, 3 level, 4 level. Okay, delta n 1, 1 to 2, difference is 1, it is allowed. 1 to 3 is not allowed. Why? Difference is 3 minus 1. 3 minus 1 is 2. It's an even number. It is not allowed. So 1 to 2, right? Then 2 to 3, 3 to 4, these are all allowed. Okay, so keep this. This is a very important formula. Then one more. This is very, very important one. Based on this, questions were already appeared. Okay, probability of finding the particle in 1D box in the region L by 4 and 3L by 4. Okay, what is the probability of finding the particle in a 1D box in the region L by 4 to 3L by 4? Listen, see, in particle in 1D box, okay, this is 0, this is where at this point x value is L, middle, at the middle L by 2. Listen, now you take this point L by 4, okay, and this point 3L by 4. Between these two limits, what is the total probability? Okay, probability of finding the particle in 1D box in the region L by 4 to 3L by 4. Okay, what is the formula for that? The formula is P is equal to 1 by 2 if N is even. Very important. Okay, if you measure probability between L by 4 to 3L by 4 for any even state, that is N equal to 2 state, N equal to 4 state, N equal to 6 state, then probability is always half. Suppose if N is odd, then we must use this formula to find the probability. Probability equal to half plus minus 1 power k by n pi. Okay, what is n here? N is equal to 2k plus 1, and k can take value 0, 1, 2, 3, etc. See, without derivation, I'm giving you the formula. Okay, so remember these formulas. Based on this, questions were already appeared. Okay, I'll show you then. Now, see this question. This question already appeared in the examination. The probability of finding the particle in a one-dimensional box of length L in the region between L by 4 and 3L by 4 for quantum number n equal to 1 is, okay, you know, well, n equal to 1 is an odd number. Whenever odd number is given and the limit is L by 4 to 3L by 4, so you need not do the derivations and all. You can use the shortcut formula. What is the formula? P is equal to 1 by 2 plus minus 1 power k by n pi, correct? Okay, minus 1 power k by n pi. One second. Yeah. moving. Yeah. So probability P equal to 1 by 2 plus minus 1 power k by n pi. Okay. Now listen, n value is 1. Okay, you know very well, n is equal to 2k plus 1. This is the formula. To get n as 1, we must put k as 0. Okay, if k is 0, then you'll get n as 1, right? Therefore, for n equal to 1 state, k value should be 0. Substitute this here. So you'll get the answer as 1 by 2 plus k is 0. So minus 1 power 0 by n value is 1. So 1 into pi is pi. Okay, and therefore the answer is 1 by 2 plus anything for 0 is 1 by pi. This is the answer. You need not do any derivation. Just remember this formula. Very, very important. Okay, so what's the answer? The answer is B. 1 by 2 plus 1 by pi gives you the probability of finding the particle between L by 4 and 3 by L by 4, right, in n equal to 1 state. Okay, then this is another problem asked in previous year examination. The difference in energy levels of n equal to 2 and n equal to 1 for a particle in 1D box is 6 unit of energy. Listen, difference in energy level for n equal to 2 and n equal to 1, right, for a particle in 1D box is given, which is 6 units. In the same unit, what is the difference in energy levels of n equal 3 and n equal 2? Okay, yeah, you know very well. Difference in energy formula is this 2n plus 1 into h square by 8ml square. Okay, I told you in this formula we have to substitute the lower value. So if you substitute the lower value here, okay, n equal to 1 here, you'll get 3 into h square by 8ml square, which is equal to 6, or h square by 8ml square equal to 2. The value of h square by 8ml square is 2. Now we need to find out the energy difference between n equal to 3 and n equal to 2 level. Okay, use this formula. The lower value is 2, so substitute 2 here. 2 into 2, 4, 4 plus 1, 5. So 5 into h square by 8ml square. 5 into h square by 8ml square, we found out the value is 2. So 5 into 2 is 10. So the answer is 10. Very simple. Okay, so remember this formula. This formula gives you the energy difference between adjacent levels in particle in 1D box. This problem was already appeared in the examination. Okay, then yeah, I have given answer for the problem. Next, see, difference of average values of position x for state n equal to 1 and n equal to 2 for a particle in 1D box of length L. See, they are asking difference in the position of x, average value of x, right, for n equal to 1 state and n is equal to 2 state. You know very well, okay, average value of x for any state is always L by 2. Average value of x for any state is always L by 2. So this is L by 2, this is also L by 2. So answer is 0. Very simple. Okay, remember, average value of x for any state is L by 2. Whereas all average value of x square, x cube, these are all depends on quantum number n. But under the limit n approaches infinity, I have told you, if n approaches infinity, then the formula is L square by 3 here. In the case of here, L cube by 4 when n approaches infinity. Are you able to understand? Very, very easy then. Next, boundary condition and quantization. Yeah, this is a very important one. Listen, see, in particle in 1D box, normally we take the limit as 0 to L. That means box length is L. Okay, if the limit is 0 to L, then the energy formula is n square h square by 8ml square. This is the formula we normally use for particle in 1D box. Now, see here, I have a particle which is present in 1D box. Okay, in 1D box. But what's the length? Length is same. Here and here, length is same. Same confinement. But the boundary condition is different. Here, boundary is 0 and L, whereas here, boundary is minus L by 2 and plus L by 2. Same confinement, but boundary is different, right? Whenever boundary changes, boundary condition will change and the quantization will also change. So here, if in the place of J, if you put 2n or 2n minus 1, you will get a different formula. Okay, yeah. So what I like to say here is quantization does not depend on confinement. Quantization, okay, or boundary condition leads to quantization, not the confinement. Okay, then now this is particle in a two-dimensional box with the infinite potential barrier outside. Now you have come to particle in two-dimensional box. In the case of two dimension, I'll take x and y axis. So particle is moving in this plane, right? And the particle is arrested, okay, in this limit. So it can move only in this area. Particle can move only in this area. Inside the box, potential energy, right, is a constant. Is a constant. You can assume it as 0. Okay, but outside the box or on the box, potential energy is assumed to be infinity. If you assume like that, then wave function psi, wave function for the particle psi depends on two coordinates x and y. Okay, and you can separate the wave function into two parts. Okay, one depends on x variable, the other one depends on y variable. It is called method of separation of variable. Okay, using the method of separation of variable, we can solve the Schrodinger equation. By solving Schrodinger equation, we'll get the energy as Enx square plus ny square into h square by 8ml square, and the two wave functions x and y are these. By if you substitute these values here, you will get the wave function for the particle. Okay, remember the formula. The formula is nx square plus ny square into h square by 8ml square, and we know very well for box problem, the quantum numbers cannot take the value 0. 0 is not allowed. It can take values 1, 2, 3, 4, etc. 1, 2, 3, 4, etc. Okay, keep this in mind. Then one second. Yeah. So the quantum numbers nx and ny can take only the values 1, 2, 3, 4, etc. Now, what are the energy levels and the degeneracies? Listen, in particle in 1D box, okay, all the levels, all the energy levels have only one state. Okay, here we have one state, here we have one state. One state means one wave function, one wave function, one wave function, right? Whereas if you go to particle in 2D box, okay, degeneracy come into play. Okay, listen, what is meant by that? See, if I put nx and ny as 1, 1, okay, in the formula, see what is the formula? Formula is this nx square plus ny square into h square by 8ml square. In the formula, if you put nx as 1 and ny as 1, you will get the energy as 2h square by 8ml square. And 1 comma 1, this is the only possible way for this particular level. So this level has only one state. If any energy level has only one state, we call that state as non-degenerate state or non-degenerate level. Okay. Now, if you go to the next level, there is excited level. Listen, in the exit level, you put nx as 2, ny as 1. Nx as 2, nx, ny. If you put nx as 2 and ny as 1, then I will get the energy as, see, nx, if you put 2 here, 2 square is 4, ny is 1, so 1 square is 1, so I'll get 5h square by 2 square, right? Suppose if we put nx as 1 and ny as 2, then also we'll get the same energy. So the state 2 comma 1 and 1 comma 2, they corresponds to the same energy 5 into h square by 8ml square. Okay, and this level is a non-degenerate, is a doubly degenerate level. Okay, because for this level, for this state, we have a wave function, say psi 2. For this state, we have a wave function psi 3. This is psi 1. Okay, listen, psi 2 and psi 3, they have different wave functions, but they have same energy. So degeneracy means that the different states having same energy, but they have different wave functions. Okay, so here this level is doubly degenerate level, which has two states. Okay, similarly we have 2 comma 2, 3 comma 1, 1 comma 3, like that we have so many states. Okay, listen, here I forgot to say one thing. Here the confinement is such that, okay, in the x direction as well as in the y direction, okay, the particle is confined with the same length. Okay, this is L, this is also L. So it is a perfect square box. In perfect square box, okay, the energy formula is this. In perfect square box, this is the energy formula, and these are all the energy levels. Okay, then. Then okay, then next. Okay, this is very, very important. Based on this, many questions have appeared in the examination. Suppose if I extend the box, if I disturb the box, okay, in any one direction. So I'm going to elongate, say for example, I'm elongating the box along the x-axis. Okay, so now the length A is larger, okay, compared to the length B. Right now it is not a perfect square box. Now it become a rectangular square box, a rectangular box, I'm sorry. For rectangular box, you'll get the energy formula like this: nx square h square by 8 m a square, right? Plus ny square h square by 8 m b square. Are you able to follow? Yeah. For square box, the formula is this: E is equal to nx square plus ny square h square by 8 m l square. Okay, this is applicable for square box. For rectangular box, okay, the formula will change like this. Now observe this carefully. Listen. If I take nx as 1, ny as 1, I will get the ground state 1, 1. Now, if I take 2, 1 state, that is nx as 2, ny as 1, and nx as 1, ny as 2. Listen, in the case of square box, these two states have same energy. But now, in the case of rectangular box, the two states, they do not have same energy. Actually, in which direction you are extending? You are elongating in x-axis. Therefore, the nx quantum number, if it is get higher value, listen, in the two state, in which state nx has higher value, see, that state will go to lower energy. See here, in the square box, A and B are equal. So the 2, 1 state and 1, 2 states are degenerate. But if A is greater than B, what is A? A is length along x-axis. Okay, if you elongate the box along x-axis, then see the nx quantum number. Okay, in the two state, this state has nx quantum number higher value. If nx has higher value, that state will go down. So actually both the state will go down, but the 2, state will go to lower energy compared to 1, 2 state. Now, which is the first excited state? The first excited state is 2, 1. Okay, be careful. You should be a little careful here because you are elongating the box along x-axis. If you elongate the box along x-axis, then the quantum number nx, the state having quantum number nx as higher value, that will come down. Okay, the quantum number nx having higher value will come down. Okay, yeah, keep this in your mind then. Yeah, this is a question appeared in the previous examination. Two opposite sides, okay, in the y direction of a square box of side L, see, a square box are slightly stretched along y direction. See, very important. Consider the following 4 statements. Okay, the point group changes from, yeah, you know very well, in the square box. For square box, point group is D4H, and for rectangular box, point group is D2H. Okay, the point group changes from D4H to D2H. Yes, correct. So the first statement is correct. See the second statement. The 1, 2 and 2, 1 energy levels remain doubly degenerate. No, it is wrong. This statement is wrong. Why? Whenever you stretch along x direction or y direction, then the two states 1 and 2 and 2, 1, 1, 2 and 2, 1, the two state never be degenerate. Okay. Both the energy levels are lowered and the energy of the 1, 2 level is higher than that of 2, 1 level. See, we are elongating in y direction. So the quantum number ny having higher value, that should go down. But it is given that it is here it is given that the energy of the 1, 2 level is higher. So this is also wrong. So you see here third T statement, both energy levels are lowered and the energy of the 1, 2 level, yeah, 1, 2 is lower than 2, 1. Yes, this is correct statement and this is also correct statement. So the correct statements are A and D, option D. Very simple question. Okay, listen, in which direction you are elongating the box? See that. Okay, suppose if you elongate the box in y direction, then the quantum state having higher value of ny will go to lower energy. Okay, then This is another question asked in the previous examination based on the same concept. For a particle of mass m confined in a rectangular box with the size 2a and a, the energy and degeneracy of the first excited state respectively are. Okay, they are not asking ground state, they are asking first excited state. Okay, so for rectangular box, the first excited state should be either 2 comma 1 or 1 comma 2. Okay, listen, suppose if there is no distortion, what will be the energy of this? The energy of this should be 5h square by 8 ml square. Okay, energy. Okay, I'll show in the next page. See, if both sides are equal, then 2 comma 1, 1 comma 2, both are degenerate. Okay, but when you do elongation or when you do distortion, right, what happens? Listen, this is supposed to be the energy when they are degenerate, when they do not undergo any distortion. Okay, 5h square by 8 ml square. Now see the options. In option 3 we have I'm sorry, see here in option 4 we have 5h square by 8 ml square or 8 ma square. So this option should be definitely wrong. Why? If there is no distortion, this should be the answer. Since there is distortion, this cannot be the answer. Okay, so remove it. Then see, they are asking two things. First excited state, right? They are asking the energy and the degeneracy of the first excited state. Listen, now after distortion, these two states never be degenerate. Okay, so they become non-degenerate. So definitely these two answers are wrong because it is given W degenerate. These two answers are wrong. So you have to decide within these two. Okay, and listen, you are elongating the box in such a manner that one side length, okay, is just twice the other side length. Okay, if you do so, what will happen? See, if you do so, what will happen? I am going to substitute the values. Okay, for 2 comma 1 state, if you calculate the energy, right, where nx is 2, so nx square is 4h square by 8m, a value is 2a now. Okay, so if you substitute, you will get the energy as 2h square by 8ma square. For 1 comma 2 state, you will get the energy, just substitute, you will get the energy as 4.25 into h square by 8m square. Now if you compare these two, listen, this is okay, here we have h square by 8 ml square as common for the two states, and here we have 2, here we have 4.25. So it indicates 2 comma 1 state should be the lower energy state. So 2 comma 1 should be the lower energy state. Are you able to follow? And the energy of that state is 2h square by 8 ma square. Okay, we have calculated using the expressions. So the correct answer, the correct answer for this question is this. Degeneracy is 1 and the energy is 2h square by 8 ma square. Okay, then now we'll come to particle in 3D box with infinite potential barrier outside. Okay, so it's a perfect cubical box. The x-axis length, y-axis length, and z-axis length all are equal. So it is a perfect cubical box. In the case of perfect cubical box, okay, the wave function depends on the three variable x, y, z, and you'll get the energy expression as nx square plus ny square plus nz square into h square by 8 ml square. Okay, then, and these are all the wave functions for x and y and z. If you multiply these three, you'll get the total wave function. Okay, yeah. I'm not going to discuss derivations and all. I'm giving you only the final expressions and the importance. Okay. So for perfect cubical box, the lowest level corresponds to nx equal to 1, ny equal to 1, nz equal to 1. So it is a non-degenerate state. Whereas if you go to the next excited level, okay, so nx, ny, nz, right, you can put nx as 2, ny as 1, nz as 1. Okay, you'll get the energy as 4 plus 1 plus 1, you'll get energy as 6h square by 8 ml square. Suppose if you take 1 comma 2 comma 1 state, for this also you'll get the same energy. Similarly, 1 comma 1 comma 2 state, this will also have same energy. So these three states, 2 comma 1 comma 1, 1 comma 2 comma 1, 1 comma 1 comma 2, all these three states have same energy. So it is called a triply degenerate state. Are you able to understand what is degeneracy? Degeneracy is nothing but number of states, okay, available for the given electronic, for the given energy E. Okay, for the given energy level E, how many states are available? All these states have same energy, but their wave functions are different. Okay, keep this in your mind. Then, and see, this is very important. What is the difference between the ground level and the first exit level? Okay, the difference between ground level and first exit level is 3h square by 8 ml square. Why I am saying this? This is for particle in 3D box. If you go to particle in 2D box, you will get the same answer for this 3 into h square by 8 ml square. This is a perfect cubical box. This is perfect square box, square. And if you go to one-dimensional box, E2 minus E1, you will get again the same answer. So that's why this is very, very important. This is not applicable for all the levels. Okay, it is applicable for the level E2 and E1. The energy difference between E2 minus E1 is 3h square by 8 ml square for cubical box, for square box, as well as for one-dimensional box. Okay, this is also a very important information. Next, this is another question appeared in the previous examination. A particle in a cubical box of length L has energy. Now energy is given. They're asking degeneracy. Okay, now see nx square, ny square, and nz square. That should be equal to 14. Simple. Okay, listen, you write this energy as 14 into h square by 8 ml square. Always keep h square by 8 ml square as such. See the number. Okay, that corresponds to nx square plus ny square plus nz square. So this sum should be equal to 14. This is possible. Okay, for the numbers 1, 2, 3. Correct. 1 square is 1, 2 square is 4, 3 square is 9. If you add, you will get the answer as 14. So for this, we have 6 possibilities actually. Keep 1 front, 3, 2. This is another state. Then keep 2 front, 1, 3, 2, 3, 1. Then 3, 1, 2. Then 3, 2, 1. So how many states? 1, 2, 3, 4, 5, 6 states are possible for this energy 14h square by 8 ml square. Therefore, the degeneracy of this state is 6. Okay, degeneracy is nothing but, right, how many possible states, okay, have the energy, have the given energy E. Okay, so here the given energy is 14h square by 8 ml square. Okay, so 6 different states have the energy 14h square by 8 ml square. Therefore, degeneracy is 6. Okay, then this is another problem. Now energy is given as 27h square by 8 ml square. Listen, to get 27, okay, nx square, ny square, nz square should be equal to 27. People normally use some numbers and they'll find out, okay, 5, 1, 1, say 25 plus 1 plus 1, 27, 1, 5, 1, 1, 1, 5. Then they stop immediately here and they'll say simply the answer is 3. But you have to think, okay, in out of box way, right? See, normally if you do calculation, we normally stop here and we'll say simply the answer is 3, right? Listen, 3, 3, 3 will also give 27. Okay, so you must be a little careful in calculating degeneracy for a particle in cubical box. Okay, so for this energy level, okay, 4 states are possible. So degeneracy is 4. Okay, then see, this question I have given an answer already. So you just do yourself. Okay, I have given answer already. I have given answer. You try to find out the answer for this question. I just leave it to you. Okay, then the answer is available here. The next system is rigid rotor. What is rigid rotor? Rigid rotor is a body. Okay, or I will take a diatomic molecule, right? If the internuclear distance between the two atoms, if it remains constant, if it remains constant during rotation, okay, if during rotation of this diatomic molecule, if internuclear distance remains constant, you can assume that diatomic molecule as a rigid rotor. So what is the idea is rigid rotor means internuclear distance should be constant. And remember, whenever R is constant, internuclear distance is constant, then potential energy also become constant. Whenever internuclear distance is constant, potential energy also become constant. When potential is constant, you can assume it as 0. So we are going to assume potential energy as 0 for rigid rotor cases. Okay. Now we can have two important rotations: rigid rotor in 2 dimension, rigid rotor in 3 dimension. What is meant by this? Yeah, rigid rotor in 2 dimension. Okay, listen, this is very important. See, if I take a diatomic molecule, here I have diatomic molecule is a 2-body problem, right? It's a 2-body problem. Schrodinger equation cannot be solved exactly for 2-body problems. We cannot solve. We can solve only system containing only 1 body. So what we have to do? See, Schrodinger equation cannot be solved. Okay, very important. So somehow we have to convert this 2-body problem into 1-body problem, single body problem. Yes, in mathematics we have that provision. Using that provision, okay, that is we have to convert the Cartesian coordinates of the system into center of mass coordinate and the internal coordinate. So if you convert the Cartesian coordinates into center of mass coordinate and internal coordinate, then the 2-body problem become a single body problem. And mass of that body is not m1 and m1 or m2. It is now called reduced mass mu. What is mu? Mu is m1 into m2 by m1 plus m2. Okay, it becomes reduced mass. Now, listen, here the diatomic molecule is rotating. Now we have converted the 2-body problem into 1-body problem. Now, if you take 1 body, that means it is moving around a circle, right? So we can call it as particle on a ring or particle on a circle with the constant radius r. Are you able to understand? Now, this particle is revolving in a ring, okay, which is present in the plane x and y. So the particle is moving in the plane x, y, and y, and z-axis is perpendicular to the ring. Okay. In this case, the wave function for the particle, say I'll represent the wave function as phi. This is the usual representation. The wave function depends on, okay, listen, it does not depend on r because r is constant. It does not depend on the variable theta. Why? Because z-axis, the angle between z-axis and the line joining the particle to the origin, this angle is actually called theta. Since this particle is moving only in xy plane, okay, theta remains constant. Therefore, wave function depends only on one variable phi. What is phi? Phi is nothing but, okay, the angle between plus x-axis to the line joining the particle and the center point. Okay, this angle is called phi angle. Okay, so in the case of rigid rotor in 2 dimension, why it is called 2 dimension? Because the particle is moving only in xy plane. And listen, the z-axis here, z-axis is actually the axis of rotation. Z-axis is called axis of rotation here. Since the particles keep on moving, right, in the xy plane, right, with the constant radius r, this axis of rotation, that is z-axis, remains in the same position. That is why it is called fixed axis rotation. So rigid rotor in 2 dimension can also be called as fixed axis rotation. Okay. Now we can solve the Schrodinger equation for the system. If you solve that, you'll get the wave function as this, and you'll get the energy as this. Okay. Here we have a quantum number ml, and ml can take value 0, plus or minus 1, plus or minus 2, etc. If I put ml as 0, I'll get the energy as 0. If ml is 0, I'll get energy as 0. What does it indicate? It indicates that, see, particle is not moving. If particle doesn't move on the ring, right, then the energy of the particle, right, is 0. Okay. Then if I put ml equal to plus 1 or minus 1, since we have ml square here, ml plus 1 and ml minus 1 will give you the same energy. Ml plus 1, ml minus 1 will give you the same energy. So this level is doubly degenerate level. Okay, what is meant by ml plus 1 and ml minus 1 indicate? Suppose if ml plus 1 is rotation in clockwise, then ml minus 1 is nothing but rotation in anti-clockwise. So a particle can revolve in clockwise direction or anti-clockwise direction, okay, right, in a particular energy level, right, or in a if the two energies are same, we call that level as doubly degenerate level. So the microscopic particle in ring, when it moves along the ring, right, it can take values, energy values like this. These are all the allowed energy levels. Okay, ml equal to 0, ml plus 1, ml minus 1, ml plus 2, ml minus 2. Here, one thing is very important. For particle in 2D box, except the ground level, all other energy levels are doubly degenerate. Keep this in your mind, very, very important. Listen, the problem may be asked in a different way. Rigid rotor in 2 dimension, fixed axis rotation, or particle on a ring, all are one and the same. Okay, for all these problems, okay, the energy level is given like this. Okay, and in this case, remember, except the ground level, all other levels are doubly degenerate. Okay, then rigid rotor in 3 dimension. What is meant by rigid rotor in 3 dimension? Suppose if the axis of the rotation does not remains in same position, if it moves, if the axis of rotation also moves, we call that rotation as rigid rotation in 3 dimension. Okay, normally in the examination, if a university examination, if they ask rigid rotor, okay, we will assume it has 3 dimensional rotation. Okay, so rigid rotor in 3 dimension, right? Now here I have taken a diatomic molecule as usual, but two-body problem cannot be, for two-body problem, Schrodinger equation cannot be solved. So we have to convert the two-body problem into one-body problem. And here the mass of this body is now mu. Now in this case, the wave function which I am going to represent as y. Okay, the wave function depends on the variables, okay, theta and phi. Here r is constant again. R is constant. So the wave function y, which is also called spherical harmonics, which depends on two variables, theta and phi. Okay, as we are running short of time, I like to give this information and stop. So in this case, you'll get the spherical harmonic function as this. Okay, here we need to use one important polynomial called associated Legendre polynomial. Okay, this is a rigid rotor system, so Legendre polynomial we should use. For harmonic oscillator, we should use Hermite polynomial. Okay, so by using associated Legendre polynomial, we can find the wave function as well as the energy of the system. So this is the energy for a particle in for a rigid rotor in 3 dimension. Rigid rotor in 3 dimension can also be called as particle on a sphere. Okay, both are one and the same. And in 2 dimension, I told you, except ground level, all other levels are doubly degenerate. Whereas for particle in 3D, for a rigid rotor in 3 dimension, okay, the degeneracy depends upon the value of L. Okay, and L can take values 0, 1, 2, 3, 4, etc. Okay, for a given value of L, there are different possible values of ML. ML can take value 0, plus or minus 1, plus or minus 2, plus or minus up to plus or minus L. Then, okay, let me run through the slides quickly. So these are all the energy levels possible. For this, the degeneracy is 1. For this, the degeneracy is 3. Degeneracy formula I gave already. For this, the degeneracy is 5. So as we move to higher level, higher energy level, degeneracy increasing. Whereas in the case of rigid rotor in 2 dimension, except the ground level, all other levels are doubly degenerate. Okay, so keep this in mind, very important. And one more information here, isn't the sum of wave functions corresponds to these states. Okay, for this energy level, the wave functions corresponds to these energy states. See, y 1 comma plus 1 square. Okay, I'll take sum of this, right? Summation is not there. Then y 1 comma 0 state square plus y 1 comma minus 1 state square. If I take the square of all these things, that is actually a constant. It's a very important conclusion. And the value of this is 2L plus 1 by 4 pi. This is the value of the constant. This question was not asked in the exam till now. Listen, square of the harmonic function, the functions, right, corresponds to the degenerate levels, degenerate states, right? If you add the square of these functions, okay, that value is a constant. and this is called unsolved theorem. This is called unsolved theorem. Okay, till now no question was asked from this, so keep this in your mind, very important. Okay, then quantization of angular momentum, I'll just leave these things. These are some simple concepts. Then simple harmonic oscillation. Okay, so in the case of diatomic molecule, right, the equilibrium length is L0. It may undergo elongation or compression. When elongation compression occurs, you'll get different values of the internuclear distance. So we need to find out the displacement. Displacement is nothing but L minus equilibrium length L0. So L minus L0 will give you displacement. In the elongation, X is positive. In compression, the X is negative. So in this case, X gives you the displacement from the equilibrium equilibrium distance. Now, see, again, it is a two-body problem we cannot solve. So we have to convert the two-body problem into one-body problem. Right? For one-body problem, we can solve the Schrodinger equation. And in this case, internuclear distance is not constant. Internuclear distance is changing during oscillation. Therefore, potential energy is not constant. Potential energy is given by the Hooke's law, which we can derive from Hooke's law. V is equal to kx square by 2. Okay, and by solving the Schrodinger equation, we can find the energy values. We can find the energy value for the system. So this is the wave function for a simple one-dimensional simple harmonic oscillator problem. This is the wave function. Okay, which involves Hermite polynomial. Right, I don't want to go into the details of all these things. Okay, but I like to say one thing which is very important. Just remember energy and the ground state wave function for simple harmonic oscillator. Often this questions are asked based on the ground state wave function. Okay, so the ground state wave function is alpha by pi whole power 1 by 4 into e power minus alpha x square by 2. In some book, instead of alpha, they'll give some beta also. Okay, it depends upon how you assume alpha and beta. Okay, so remember the ground state wave function, which is very important, and the energy formula. And here, if you put n as 0, these are the possible value of n. If you put n is equal to 0, even n is 0, okay, the energy is not 0. Okay, you will get some energy, and even if you put n equals 0, you will get some energy which is half h nu. Okay, it is called 0 point energy. Okay, 0 point energy for the system. Then, so this is the ground state wave function I gave already, and these are all energy levels. And in the case of one-dimensional simple harmonic oscillator, okay, the gap between adjacent levels are equal. Keep this in mind, very important. Okay, then, and these are all the wave functions. Okay, I'll discuss this question. The correct statement about the symmetry of the eigenfunctions of a quantum of 1D harmonic oscillator is all the eigenfunctions are only even functions because the potential is an even function. Okay, listen. To find the parity, use this rule -1 power n. This is for one-dimensional simple harmonic oscillator. Suppose if three-dimensional simple harmonic oscillator is given, three-dimensional, because in the last few years problems people are asking problems from three-dimensional simple harmonic oscillators. For three-dimensional simple harmonic oscillator, to find the parity, we should use the formula -1 power nx plus ny plus nz. Okay, so if you want to find the parity of the ground state, put n equals 0 here. If n equals 0, I'll get the answer as 1. Okay, I'll get the answer as 1. So that means n is equal to 0 is an even function. Okay, yeah, it's an even function. Then if you put n equal to 1, right, I'll get the answer as -1. Okay, if I get -1, right, see, if I get +1, repeat here. Yeah, if you put n is equal to 1, n equals 0 is the ground state. No, if you put n equals 0, I'll get pi s plus 1. Pi plus 1 means it is even function. If you put n equal to 1 here, -1 power 1 is -1. So if pi is parity is -1, that wave function is an odd function. So ground wave function is even. The next excited wave function, first excited wave function is odd. If you go to the second excited wave function, that is again even. So you'll get the repetition, even, odd, even, odd, even, odd. Listen, if you get odd, even, odd, even, odd, even like that, okay, odd, then even, odd, then even, then odd, then even like that, it represents that potential energy should be an even function. See, very important. Whenever potential energy x square is there, see, whenever potential energy is an even function, then the wave functions corresponds to these states, okay, will repeat like odd, even, odd, even, odd, even like that. Okay, if v is not even function, if it is an odd function, then all these functions should be either odd or all the functions should be either even. Okay, so keep this in mind. So all the eigenfunctions are only even. It is wrong. Why? Because for 1D box, okay, potential energy is an even function. Okay, so this is wrong. Second option, all the eigenfunctions are only odd. That is also wrong. The eigenfunctions have no odd even parity symmetry. No. All the eigenfunctions are either odd or even functions because the potential energy is an even function. Yes, that's correct. Okay, you will get odd, even, odd, even, odd, even like that. Okay, because potential energy is an even function. Right, next. Okay, I'll give this information, then I stop. For three-dimensional harmonic oscillator, okay, this is the energy formula. Okay, suppose if the frequencies along x-axis, y-axis, and z-axis are same, if the frequencies are same, then we call that three-dimensional harmonic oscillator as isotropic oscillator. For isotropic oscillator, the energy formula is this: nx plus ny plus nz plus 3/2 h nu. This is the formula. And what is the 0 point energy here? Listen, put nx as 0, ny as 0, and nz as 0. If all these values are 0, then you'll get 3/2 h nu. This is the 0 point energy for isotropic oscillator. I repeat, what is isotropic oscillator? Isotropic oscillator is a three-dimensional oscillator, okay, for which the frequencies along x-axis, y-axis, and z-axis are same. Okay. Hello, madam. Shall I continue, madam, or?
I think we are running out of time, sir.
Okay, okay, madam. Then I stop here, madam.
Yes, sir.
Yeah.
Thank you, sir.
Thank you, madam. Thank you.
How many more are there, sir?
I think we need to see hydrogen atom, madam. Hydrogen atom problem. Let's see.
Hydrogen atom problem. Another 5 minutes, sir?
I think so, madam. It will complete.
Yes, sir.
I'll try to complete 5 minutes.
Finish off, sir. Finish off, sir.
Okay, okay, madam. Thank you. Thank you, madam.
हेलो नहीं और कितना देर होगा करकर इसलिए नहीं बोल दिया उन्होंने 5 मिनट होगा कर
Okay. So let me discuss hydrogen atom problem now. Hydrogen atom in the absence of external field. Listen, in the absence of any external electric field or magnetic field, then the Schrodinger equation for hydrogen atom can be solved. But again, there's a problem that in hydrogen atom we have a nucleus and we have an electron. It is a two-body problem. Two-body problem. For two-body problem, Schrodinger equation cannot be solved. So we have to convert the two-body problem into one body. Okay. So now this one body, right? A single body having mass mu, and mu is equal to, in this case, mu is equal to mass of the electron into mass of the proton by mass of electron plus mass of proton. You know very well, in hydrogen atom, the nucleus consists only proton. Therefore, so instead of mass of nucleus, here I have taken mass of proton. Okay. Now, listen, you know very well, mass of proton is roughly 1837 times larger than the mass of electron. So roughly 2000 times. Therefore, if you compare mass of electron and mass of proton, since mass of proton is very heavy, you can neglect the mass of electron here. If you neglect here, you will get Me into Mp by Mp. Mp get cancelled. So mu is nothing but mass of electron. Okay, so this is very, very important. Mu is almost equal to the mass of electron. We cannot say exactly, almost equal to mass of electron. Okay, then. So in some book, instead of mu, people will use mass of electron. Nothing wrong in it. That is also correct. Okay. Then. So this is the Schrodinger equation. Listen here. We have translational motion and relative motion. Okay, relative motion corresponds to electronic energy, right? So we are assuming that hydrogen atom, the entire movement of hydrogen atom, right, will give you translation motion. Since we have already discussed about translation motion, okay, we are going to concentrate only on the relative motion, also called electronic energy. So I am going to solve the electronic part of the Schrodinger equation, not the total Schrodinger equation. Okay, so by solving the electronic Schrodinger equation, you will get the wave function. Wave function has three parts now: radial part, theta part, and phi part. Here, I'd like to say one thing which is very, very important. See here, the limit of R. R limit is 0 to infinity. Okay, so we can say that, so whether it is confined or not. Yes, it is confined for a value of 0 to infinity, very large confinement. Okay, listen, if you do confinement in R, see 0 to, some people may confine this to some value A naught, also called Bohr radius. If you confine along R, okay, we call that type of system as a special system, spherically confined systems. We are not going to discuss spherically confined system here. We are going to discuss just hydrogen atom, okay, with the limit that R is equal to 0 to infinity. Okay, so if you solve, you will get the electronic energy like this, and if you substitute the values, okay, you will get the electronic energy as minus 13.6 by n square into z square electron volt per atom, which is exactly the same as the Bohr gave for hydrogen atom. Okay, exactly same formula. So yes, the Bohr's prediction and the Schrodinger solution of the Schrodinger equation are one and the same for hydrogen atom alone. Okay, then here n can take value 1, 2, 3, 4, etc. L can take value 0, 1, 2, up to n minus 1, and these are all the possible ML values. N is called principal quantum number, azimuthal quantum number, and magnetic quantum numbers. And listen, spin quantum number. Okay, listen, spin quantum number never arises from quantum in Schrodinger equation. It is not arises by solving Schrodinger equation. It arises due to some other reasons. Okay, I cannot go into the details of all. So I'll just give that information. So the energy corresponds to n equal to 1 for hydrogen atom in the ground state is minus 13.6 electron volt. Okay, see what is ground state? For ground state, n value is 1. If n is 1, the possible value of L is 0. If L is 0, then the possible value of ML also 0. This is N, L, this is ML. Okay, similarly, when n is equal to 1, we have 4 possible values. What are the 4 possibilities? L can be 0, L can be 1. Okay, and when L is 0, the only possible value of ML is 0. When L is 1, there are 3 possible values of ML. What are they? Plus 1, 0, minus 1. So degeneracy of this level is 4 without including spin state. Keep this in your mind. I am not including spin state. Okay, these are all states arises due to orbitals. Okay, so degeneracy, orbital degeneracies, these are all. Okay, orbital degeneracy is 4. Okay, then not the spin degeneracy. Spin degeneracy is different. Similarly, for n equal 3, we'll get degeneracy as 9. Right, as we go to higher level, what will happen? These levels starts to merge up, and okay, and at when n approaches infinity, you will get continuum state. Quantization disappears. I repeat, quantization appears only for lower value of n. If you go to very high value of n, the quantization disappears. You will get the quantum mechanics and classical mechanics merges. Okay, yeah, then. Okay, I'll discuss this problem and we'll stop. The most probable value of R for an electron in 1s orbital of hydrogen atom. Listen, 1s orbital, you know very well, if you plot radial function, right, or R square, radial function versus R, you'll get single peak. Okay, for 1s orbital. Similarly, for 2p orbital, you'll get a single peak. Similarly, for 3d orbital, you'll get a single peak. whenever you get single peak, okay, in the radial probability plot, then to find the most probable position of the electron, okay, we can use this formula n square a naught by z. I repeat, this is z. This formula is applicable only for orbitals for which the radial probability plot has only one peak. If you have only one peak, then you can use this formula. So you can use this formula for 1s orbital, 2p orbital, 3d orbital, 4f orbital, etc. Okay. So now for 1s orbital, value of n is 1. Value of n is 1. So 1 square is 1. A naught by hydrogen atom. The hydrogen atom Z value is 1. So the answer is A naught. The most probable distance, okay, from nucleus, right, is A naught for hydrogen atom. Similarly, other problems are there. So some more problems are asked in the examination based on this. You just go through. Okay, stop here. Okay. Thank you, madam. I stop here. Participants, if you have any questions, I will be happy.
Yes, sir. Uh, Thank you so much, sir, for explaining this complex quantum mechanical concepts in a very simple manner. And also, I thank you for explaining the solutions for few CSCR questions, sir. Thank you so much, sir. And
Thank
I
you, madam.
think the participants would have definitely benefited out of this. There are a few
Thank you,
questions
madam.
posted in the chat box, sir.
Yes, madam.
Wanted to know, is this concepts enough for the CSCR preparation?
Almost I have discussed, madam, but they have to prepare some more. This is not actually sufficient.
Yes, sir.
Madam, am I giving the answer correctly for your question?
Yes, sir. Because one participant, Dhanalakshmi, wanted to know whether only studying these concepts would be enough for them to clear the questions from quantum mechanics. So,
Yeah, actually, I have introduced some basic ideas only, madam. But they have to go through some books that is available in market.
yes, sir.
Please start with if you are interested in quantum mechanics, please start with the quantum chemistry by Donald Macquarie. Lot of informations are there. Okay, then quantum chemistry by Indian author Dua. She madam also written some book. So just go through. Lot of information are there, but the information that I gave today, okay, will give you the entry level of learning quantum chemistry. That's all.
Yes, sir.
Okay.
Another participant wanted to know regarding the question number 8 that you had explained. Why not the answer is option number 2 for question number 8?
Question number 8, madam. 1 second.
Yes, sir.
Question number 8. 1 second. Yes.
Yes, sir.
What's the
The
question, madam?
participant
Why
is
not?
asking why the answer cannot be option number 2.
Yeah, here I have assumed that 2a as along x-axis and a as y-axis. Okay, and answer 2 cannot be because degeneracy is given as 2 here. See this. When you distort a square box and make it into rectangular box, okay, then the 2 comma 1 state and 1 comma 2 state never be degenerate. Okay, the degeneracy is lifted, so you'll get 2 states now, 2 non-degenerate states. So it cannot be doubly degenerate. So answer 2 cannot be the answer for the question.
Yes, sir.
Yes,
Thank you,
right?
sir. Thanks.
Thank you.
The participants wanted to know the name of the reference books. They are just asking you to give the name of the reference books once again, sir.
Okay, I'll give madam a few books. Quantum Chemistry by Donald A. Macquarie. Participants, if you want, I'll write. I'll write once again. Quantum chemistry. I just put QC. Quantum chemistry.
Yes, sir.
Donald Macquarie. Donald A. Macquarie. It's a very nice book. To start with, we can use this. Then we have quantum chemistry written by two authors. I don't remember the exact name of the Dua something it comes. She's an Indian author. This book is also very good, madam. Then quantum chemistry by Ira and Levin. Then quantum chemistry by R.K. Prasad. And this book is not available in market. If you get, you'll be really lucky. Madan Patania. This book is right now it's not available in the market. Okay, if it is available, you can use. All these books are very interesting one. And this book is somewhat little difficult, so don't start with quantum chemistry by Ira and Levin. Always start with quantum chemistry by Donald Macquarie. You'll get some clarity in the subject. After that, you can go through quantum chemistry by Ira and Levin.
Yes, sir. Thank you so much, sir, for such a wonderful presentation. We have come to the end of the session. It was really a very wonderful session, sir. Thank you so much, sir. I now request Dr. Tamre Selvi, Assistant Professor, Department of Chemistry. Thanks.
Thank you, Sandhya. Good afternoon to one and all. It's my privilege to propose the vote of thanks for today's session. First and foremost, I, on behalf of Department of Chemistry and IQAC, would like to thank our management, Punjab Association, and our principal, Dr. R. Shanti, for their support. I wholeheartedly thank Dr. Jayashree Ghosh, Director, Management Studies, Adarsh College for Women, for her constant motivation. I thank Mr. Gopalakrishnan, Assistant Professor, Department of Chemistry, DG Vaishnav College, for his informative lecture. Here, I would like to quote Harry Wong, an educational speaker. In an effective classroom, students should not only know what they are doing, they should also know why and how. I'm sure after the session, participants would have understood the nuances of quantum mechanics very well. Thank you, sir. My thanks are due to Dr. S. Shanti, Head, Department of Chemistry, without whose guidance this webinar would not have materialized. I thank all the faculty members of the department for their tireless effort and support. I thank all the students of the department for the enthusiasm they have shown throughout this webinar series. I will be failing in my duties if I don't thank the Department of Computer Science, Mrs. Jasmine, and Mr. Saravanan for providing the technical support. Last but not the least, I thank all the participants who joined us for today's session. Thank you, one and all.
Thank you, ma'am.
Thank you, madam.
Yeah, thank you so much, sir.
Thank you, madam. Thank you, madam.
Instructions to the participants.
Excuse me, madam. Shall I leave, madam?
Yes, sir. Yes, sir. Thank you so much, sir. Thank you, sir.
Madam. Thank you, madam.
Thank you, sir. Thank you.
Thank you, madam.
Participants, the feedback link will be posted now. Please fill the feedback link before you leave the platform. The feedback link is posted in the chat box. Kindly fill the feedback form with utmost care as the certificates are auto-generated. Once you fill in the feedback form, you can leave the platform. Tomorrow, we have an interesting session on pericyclic reactions by Professor S. Varnalakshmi, retired Professor of Chemistry at Guru Nanak College. Kindly join us for the session before 10 a.m. tomorrow. Looking forward for your participation for the last day of the webinar series tomorrow. The feedback link is posted in the chat box. Kindly fill the feedback form. The feedback link is posted in the chat box. Kindly fill the feedback form with care. As the certificates are auto-generated, please don't make any mistakes while filling up the feedback.